Montgomery, who mainly does celestial mechanics, but I did a combination of billiards and celestial mechanics, and that sort of put me down this path of working in billiards. So a quick outline of everything that I'll be talking about today is that we'll start with sort of an introduction with a bunch of with a review of a bunch of the basics from billiards, and then we'll specifically talk about Birkhoff billiards, and then transition over to magnetic billiards and what we call inverse magnetic billiards. And the main goals are going to be to compare magnetic billiards and inverse magnetic billiards to Birkhoff billiards and see what's the same and what's different, because as we know, billiards is a very it's a very broad subject and has lots of fun applications. This is my first time giving a talk like this on Zoom, and so when this is all said and done, if anyone has any comments or feedback, I'd love to hear what you have to say. And if you have any questions along the way, you can either put them in the chat or unmute yourself and ask them, and I'll do what I can to answer your questions. So to start, mathematical billiards is going to be a very simple dynamical system where we consider a connected set that we call the billiard table and a point mass on its interior that we call the billiard ball. And we assume that it moves in a straight line with constant speed. When the ball hits the boundary, it reflects elastically. It satisfies the rule angle of incidence equals angle of reflection. And in physics, sometimes this is seen as conservation of energy and conservation of linear momentum. And as you can see, we can get some very nice pictures here too. So when it comes to billiards, one main observation is that in between bounces with the boundary, that there isn't a whole lot going on. The position is changing, but the velocity vector is not. And so when it comes to understanding the dynamics, all we really need to know is where this billiard ball is going to be hitting on the boundary. So for example, if we're starting at any point P on the boundary of our rectangular table here, to know where this billiard is going to hit next, we really only need to know the angle theta that it makes with the wall. And so based on our picture here, our angle can be anything between 0 and pi. So when we want to talk about a billiard map, this billiard map is going to be a map that sends every point P and its angle theta that it makes with the wall to the corresponding point P prime and theta prime, the point of the next collision, and the angle of reflection of that next collision point. We can define it as being a map from the annulus, the boundary of this rectangle R across 0 pi to itself. And the thing that we notice is that at least in terms of the previous picture, that the dynamics is very much determined by what happens in terms of the shape of the boundary. So if we have simple shapes like a circle or an ellipse, we can see what happens there, or we can have billiard tables that also are polygonal, not necessarily convex. They can be algebraic curves, but we want to make sure that for our purposes, we're going to choose a bit later on that our boundaries are going to be sufficiently smooth so there won't be cusps or corners like we see in the bottom two tables here, and that we want them to be sufficiently smooth so that curvature is defined always. Billiards can also be studied as being geodesic flow on a Riemannian manifold, but we're not going to be talking about that version of billiards today. So in the case where we do have a sufficiently smooth boundary, then the reflection law needs to be changed a little bit. So once we get to the point of reflection, we want to draw the tangent line to our billiard table and then measure the angle that our incoming velocity vector and outgoing velocity vector make with the tangent at that point. And so from that previous slide, if we have boundary curves of our table with cusps or corners, then this is where we run into some trouble. So there are lots of different types of billiards that we can discuss. Here are several polygonal billiards. When we talk about billiards inside of a polygon or a regular polygon, we can relate this to geodesic flow on a translation surface. This also has relations to Teichmuller theory. When we talk about strictly convex billiards or convex billiards, this was first studied about 90 to 100 years ago by Birkhoff, and this is often a quintessential example of a dynamical system. In this case of convex billiards, the billiard map is a twist map, which we'll talk about a bit more later. And there's also we can have regular dynamics, we have predictable periodic orbits, and there are also situations in which we can have chaotic dynamics as well. In dispersive billiards, this is where a bit more of the hyperbolicity occurs, where we can have chaotic behavior. Nearby orbits, nearby orbits can disperse far away from one another. And there are ways that we can measure this statistically. And there are several applications to statistical physics that are from these dispersive billiard tables. So for now, what we're going to focus on are these strictly convex billiards, or what we call Birkhoff billiards. So the Birkhoff billiard, this is going to be something that we're going to consider a planar table in R2 that is strictly convex, and we're going to want to parameterize the boundary of this by arc length, and we're going to consider the induced, or we're going to measure our angle of reflection in terms of the ingoing velocity vector and the positive tangent at each point of reflection. And so our billiard map now still has the same form as before, but we'll write our coordinates as SI, theta I for each arc length coordinate S, and the angle theta that it makes with a positive tangent at that point. So our map is going to be from the boundary and this angle, this inward directing angle to itself. So this billiard map that we call T1, we can think about the boundary, if it has length L, as being sort of isomorphic to R mod LZ. And so we can really consider this domain as being this open annulus, R mod LZ, across the interval 0 to pi. And so this map, if the boundary is R times differentiable, then this map itself is R minus 1 times differentiable. This map can be extended from the open annulus to the closed annulus by saying that if the angle is 0 or pi at any given point, then motion stops. So we'll just say that this is the identity map at those points. This map is symplectic. It preserves the symplectic area form. D omega is sine theta, d theta, wedge ds. And this map is a symplectic twist map. And so again, we mentioned that this has applications to KAM theory and Aubrey-Mather theory. And in particular, one thing that we'll talk about a bit later is that when a map is a symplectic twist map, that also means that there are going to be periodic orbits of every rational rotation number. When this map is a twist map, it also means that it has a unique generating function up to an additive constant. And our generating function here is going to be the negative Euclidean length between successive collisions with the boundary. So that gamma of I plus 1 minus gamma of S of I, that's just the Euclidean length of the distance the billiard traveled between reflection points. So in terms of being a generating function, this also means that this partial derivative dH dSi is going to give us cosine theta sub I, and dH dSi sub I plus 1 is going to be negative cosine theta I plus 1. And in particular, where this generating function comes into play that we're not going to talk too much about is that that this helps us find, or orbits are going to be critical points of what we call the length functional, which is a way to minimize the length between, say, 2 points, that if we have 2 points on our boundary and it needs to reflect off of a third point, if it goes from point A to, say, point B and then B to C, then the orbit that is going to minimize that length, if it has to go from A to B to C, is going to be the one that satisfies this angle of incidence, this angle of reflection. And so we won't talk too much about the length functional. That can be a talk for another day, but we want to then sort of discover or see what billiards looks like in a couple basic examples. And so the first is billiards inside of a circle. So the circular billiard was at some level first invented by Lewis Carroll of Alice in Wonderland fame in 1889. And this, he created some rules for a circular billiard game. And you can see here there's rule 1, but there are still rules 2, 3, and 4 that didn't quite fit on the screen. And it's even said that Lewis Carroll had a circular billiard table made for him in the late 1800s because of this. So in the case of the circle, the billiard map is very easy to write out explicitly. If we have a circle of radius r, then this map is just going to be, the angle theta is going to stay constant, and the position coordinate is just going to add the arc length along the boundary there, which is 2r theta, just from some clean Euclidean geometry. And so this means that theta is going to be an integral of motion in this case. So if this angle, because angle is fixed throughout this map, we can say that if theta is a rational multiple of pi, then our orbit is going to be periodic. So here we have four different periodic orbits. The first, when theta is pi over 2, this is a period 2 orbit. It's just the diameter of the circle. If theta is pi over 3, we get an equilateral triangle with period 3. Pi over 5 gets us a period 5, and 2 pi over 7 gets us a period 7 orbit. And one thing that matters a little bit here that we'll talk about more later is that in this case, we say that for every rational number p over q in this interval from 0 to 1/2, there are going to be infinitely many periodic orbits which have this rotation number p over q. And one thing that matters a little bit here is that this interval is restricted down to being from 0 to 1/2, because say, if we think about the case of this angle pi over 5, if this angle theta is instead pi minus pi divided by 5, then it's going to trace out the exact same pentagon as this orbit does. The only difference is that the direction vectors are going to be pointing in the opposite direction. And so we're going to, in some ways, consider those to be the same orbit. And so an orbit here that has rotation number 1/5 is going to have the same orbit as a trajectory that has rotation number 4/5. And in some circles, this is called time reversal symmetry. And so the billiards here does have this time reversal property that reversing the velocity is going to get us the same orbit when we have a periodic orbit like this. If theta is not a rational multiple of pi, then this trajectory is going to hit the boundary at a dense set of points. And one thing to notice is that in this picture here, that every one of the trajectories here is going to be tangent to this circle in the middle. And this circle is an example of what we call a caustic. And in billiards, understanding caustics is sort of a gateway to understanding integrability. So when we talk about caustics in billiards, a convex caustic is going to be a closed C1 curve on the inside of our billiard table, so that every trajectory that is tangent to that caustic is going to also going to be tangent to the curve. Sorry, is there a question? All right, thank you. All right, so these caustics, these curves that if a trajectory is tangent to this curve after reflection, it remains tangent. This has a lot of applications in geometry. There's a famous theorem of Poncelet that says that whenever a polygon is inscribed inside one conic and circumscribed about another, that it also has to be part of an infinite family of polygons that are all inscribed in and circumscribed about the same two conics. So this is a branch of the work that Milena does in our department. And so we're not going to talk much about this idea here, but understanding these caustics is very important. The other idea dealing with caustics is that there's always going to be an invariant circle in phase space that corresponds to this caustic. And the important note is that the converse of this isn't necessarily true, that if we have an invariant circle in phase space, this will give rise to a caustic, but it may not necessarily be convex, and it may not be differentiable. And when it comes to caustics, we certainly have this qualifier here, convex. It is possible to have caustics that are not convex, certainly ones that are not differentiable. We could also have caustics in other settings that have other qualifiers in front of them. So here we're specifically talking about convex ones. So when we want to talk about integrability in billiards, we've got a couple ways to talk about them. We can talk about Liouville-Arnold integrability when we see existence of integrals of motion. We can also talk about C0 integrability, where we have a foliation by invariant Lagrangian submanifolds. And so when we consider integrability in this setting, we're really going to be thinking about, say, C0 integrability for our purposes today. So geometrically, that means that part of our billiard table is going to be foliated by caustics. And so this diagram below here, this is a not very exciting picture of the phase space of the billiard in a circle, where the horizontal coordinate is going to be our position coordinate along the boundary, and the vertical axis is measuring the angle that the billiard makes with the tangent at that boundary. And so because the angle theta is constant, we see that our phase space really is foliated by these invariant manifolds, or these one-dimensional lines here. So when we want to talk about caustics, one thing that one might ask is talking about the existence and non-existence of caustics. So are there examples of billiards with at least one caustic? The answer is yes. There's a classical thing called the string construction, where if you have a curve, a caustic, this convex caustics down here, and you take a string that has a length that is strictly larger than the length of this caustic, and you wrap that string around the caustic and pull it taut, then the locus of all the points that you get by dragging that string around without slipping is going to give you a curve that has that given caustic as a caustic for the billiard in that table. If there are, we can also ask if there are examples of billiards that have infinitely many caustics. The answer is yes. A proof in the 70s by Lazutkin gave a coordinate change so that every Birkhoff billiard is nearly integrable when you get close to the boundary. This is using a KAM type theorem and required the boundary to be sufficiently differentiable. The very first, this proof by Lazutkin required the boundary to be 553 times differentiable, but there have certainly been improvements down to, I believe, 6. If the boundary is at least C6, then we can apply these KAM type theorems so that a Cantor set of caustics accumulate near the boundary. We can also ask if there are billiards that have no caustics. The answer is yes, if the curvature of the boundary is allowed to vanish. So if there's a point of 0 curvature on the boundary, then there will be no caustics that accumulate near the boundary. This is by a theorem of Mather from 1984. And so even though we've been talking about convex billiards, we're really talking about strictly convex billiards. And a classic example of billiards with no caustics is what's called the stadium, which is a rectangle capped by 2 semicircles. And that's shown, and that has a lot of nice chaotic properties. It's ergodic, and there are many other things done there. So then a natural question is, aside from the circle that we've already talked about, are there any other billiards that have foliations by caustics? And so that leads us to our next example of elliptical billiards. And so here we have a picture of what's called elliptipool. This is from the 1960s. The New York Times actually ran a full page ad for elliptipool, advertising this elliptical billiard table that has a pocket at a focus of the ellipse. And there was going to be a demonstration of using this table with Paul Newman and Joanne Woodward back in the day. So we're looking at here a billiard inside an ellipse. We've got these 2 blue points. We've got each focus here. And so here's an example of a billiard in an ellipse that has a caustic that is not convex. So here we have we have a hyperbola that is confocal with the original ellipse. And so this hyperbola shares a focus with the ellipse. And in fact, one small caveat here, now that this caustic is no longer convex, is that some of these trajectories, when strictly inside this ellipse, are not actually going to be tangent to this hyperbola. But if you extend them infinitely in each direction, then they will be tangent to the hyperbola, again, extending this further. And so one thing to notice here is that if we were to consider the line segment that connects one focus to the other, then this billiard is going to intersect that line segment infinitely many times. If this trajectory goes on the outside of the segment that connects one focus to the other, then the trajectory is always going to stay there. And so here we also have, now we have an example of a convex caustic, where every trajectory is going to be tangent to this ellipse, and this ellipse is confocal to the elliptical billiard table here. And in fact, if we have the billiard going through one of the focus, then after reflection, it will always go through the other focus. And this makes a fair amount of sense if you consider a geometric definition of the ellipse as being the set of all points that are a fixed distance away from 2 points. And so something like this, if you're playing elliptipool, then you know that if you need to hit it into one pocket after bouncing it off a wall, you just need to hit that billiard through the other focus, and it will reflect and go into the other through the other focus. And so as a bit of a detour, I actually had the opportunity to play on an elliptical pool table in Jyväskylä in Finland last year. In fact, this was a day before I had my interview for my postdoc here at the University of Sydney, and so I think it was a sign. So if we consider the phase portrait of the billiard inside the ellipse, this is what it looks like. Again, the horizontal axis, this is the position coordinate along the boundary. And the vertical axis, this is the angle made with the boundary, or with the tangent to the boundary at point of reflection. And so these curves at the bottom and top, these are these invariant curves. And these are sort of give us this evidence of the caustic. We can see that our phase space is sort of foliated by these invariant curves. And so this ellipse is another example of an integrable billiard. So we talked about this in the circular case, but it's also true that in the elliptical case, that for every rational p over q in the open interval from 0 to 1/2, there are going to be infinitely many periodic orbits with rotation number p over q. This can be seen as a corollary of theorems of Poincaré, Birkhoff, Aubrey-Mather, and a handful of others in various settings. There are going to be exactly 2 period 2 orbits. These are going to be the diameters of the ellipse on the major axis and the minor axis. There are going to be infinitely many convex caustics and infinitely many non-convex caustics. Those confocal ellipses and the confocal hyperbola, those are the convex caustics and non-convex caustics. And so there's a conjecture by Birkhoff in the 1930s, I believe, that where he believes that, or where he states that the only integrable billiards are going to be billiards inside of ellipses, where circles are considered as a subcase of ellipses, where the semi-major and semi-minor axes are the same length. The Portitsky here, or Portitsky, this is only because it was one of the earliest sightings of this is from Portitsky, a student of Birkhoff from the 1950s, but it was known to be a conjecture of Birkhoff before then. So now we make the transition over to these magnetic variants of billiards. So what we want to first start talking about is magnetic billiards. This was first studied by Robnik and Berry in the 1980s. And the way we consider magnetic billiards is by having a constant magnetic field orthogonal to the table. And we consider the billiard ball as being a charged particle of charge E. And so a charged particle in a uniform magnetic field like this it's subject to the force mass times acceleration is charge times velocity cross magnetic field, where that cross is the usual cross product in R3. And so what this gives us is uniform circular motion. Because our magnetic field is constant, we have circular motion of a fixed radius that we'll call mu, and mu is dependent upon both the mass, the speed, the charge, and the strength of the magnetic field. And without loss of generality, we're going to suppose that the charge times the magnetic field is going to be negative, so that motion is always going to be in the counterclockwise direction. So these magnetic billiards, we've got two examples, some with smaller angles and some with larger angles inside of an ellipse here. We can see that it still follows the same angle of incidence as angle of reflection by drawing the tangent at the point of impact. We can do the same as we did before and define the magnetic billiard map. It's still defined on the same annulus, where again, we're parameterizing the boundary by arc length. Just like the standard billiard map or the Birkhoff billiard map, if the boundary is r times differentiable, then the billiard map itself is going to be r-1 times differentiable. Just as before, we can extend this map to the identity at the boundary of its domain, where if the angle made with the boundary is 0 or pi, we consider motion to stop. This map is also symplectic. It preserves the same area form. D omega is sine theta d theta wedge ds. But what changes here is that we have what we call curvature regimes. And the dynamics is going to change dramatically based on whether the radius, that Larmor radius mu, is smaller than, in between, or larger than the minimum and maximum radii of curvature of the boundary. And so we're going to suppose that all of our boundaries here are sufficiently differentiable, it's sufficiently smooth so that our radius of curvature has a minimum and maximum. And because we're assuming that our boundaries are our tables are strictly convex, there is both a minimum and maximum radius of curvature. So in the setting for magnetic billiards, this map is sometimes a twist map. And we can state specifically that this map is only going to be a twist map whenever the Larmor radius mu of the circular arcs is going to be larger than the maximum radius of curvature. In the other two curvature regimes, it's possible that this map is not a twist map. And so a lot of the theorems from Aubrey-Mather theory and some pieces of KM theory aren't going to apply directly in that setting. So now in a change from Birkhoff billiards, when this map is a twist map, we're now going to have infinitely many periodic orbits with rotation number p over q that's now in the interval from 0 to 1. And so there's no longer this time reversal symmetry, because this magnetic billiard that goes from say this point s1 theta 1 to s2 theta 2, that reversing the velocity isn't going to retrace that circle. We would also have to reverse the velocity, and we would also have to switch the sign of the charge, so that now it will move in the clockwise direction. So just as before, when this map is a twist map, it has a unique generating function. And this map, or this generating function, is now what I've written here as negative L plus 1 over mu times S, where L is the length of the circular arc in blue, and S is going to be the area that is outside of that circular arc, but still inside of the table. So this area that's sort of shaded in brown here. And so this is our generating function, and we can still use it for the same length, or in the same sort of setting that we had talked about earlier, but it's now slightly more geometric than just straight Euclidean length. In the case of circular magnetic billiards, we can still do the same idea, where this map simplifies a whole lot and we can write down an expression explicitly for it. So this now is going to send the pair, let's see, so I've got a question here from Kara. So does L minus S mu work for general tables or just elliptic? So this generating function is for all convex tables. Yeah, so this generating function is not specific to ellipses, but this picture is just drawn for ellipses because it makes it a little bit nicer. So for circular magnetic billiards, we have a very similar process. This map can be written out explicitly as theta being a constant of motion again, but the S position, this now moves around the circle to r psi, where r is the radius of this circle, and psi is the angle made between the ingoing velocity vector and the chord that connects one point to its successive reflection point. So it's that red angle psi in the picture. And so in circular tables, this angle psi is constant and a lot of the dynamics is dependent upon this psi. And so broadly speaking, if you can get a handle on what psi is, then you have a very good understanding of what the dynamics is going to be on that table. And so the second picture on the right here is is a period 5 orbit in these magnetic billiard setting. So here's an example of magnetic billiards in an ellipse. Here, what we're looking at is these darker points in purple. These are the intersection points. These are the reflection points along the boundary. In red, we have each focus of the ellipse itself. And in orange, these are the centers of these Larmor circles. And in magnetic billiards, sometimes it can be interesting to study the map that sends, rather than the map that sends, or the billiard map, or the magnetic billiard map, it's interesting to study the map that sends one center to the center of the next circle. So here we see that there's a convex caustic. However, it's not confocal, the same way that, that we would find in standard billiards. Here's a look at our phase space when mu is less than the minimum radius of curvature. We have a lot of these invariant curves corresponding to these convex caustics. In the case when mu is in between the minimum and maximum radius of curvature, this is an example of a trajectory that is chaotic. This only has 250 iterations of the map, and if there were more, it would fill out the rest of the billiard table. This is a look at pieces of the phase space. If we were to fill in the rest of this, there are going to be more chaotic regions down at the very bottom here, and more invariant curves at the top. In the case when mu is larger than the maximum radius of curvature in this twist map setting, here's another example of having a convex caustic. And now these Larmor circles have a very large radius. And so each one of these reflection points is relatively far away from where it started, but it's still, these magnetic arcs are arcing away from the interior of our billiard table. And so here's a look at the phase portrait when mu is larger than the maximum radius of curvature. And so aside from these chaotic orbits, this is starting to look a little bit more like what we had seen for standard billiards inside an ellipse. We have these period 2 orbits in here and invariant curves up here when theta is close to pi. So just like before with Birkhoff billiards, we can ask when caustics are going to exist in magnetic billiards. So there is an analogous string construction. So if you're given a convex curve, you can create a billiard table that has that curve as a caustic. The process is a little bit more complicated, but nevertheless, it is an analog of that string construction. A theorem from Berglund and Kunz in 1995 gives, through sort of a version of the KAM theorems, that if your boundary is at least C6, then we can find caustics in several settings. If mu is smaller than the minimum radius of curvature and theta is near 0, so that the initial angle is very close to the boundary in the positive direction. Also when mu is larger than the maximum radius of curvature and theta is near 0. And for all values of mu, all radii of these magnetic arcs, if theta is sufficiently close to pi. So in these previous pictures like this one, these angles, because motion is in the counterclockwise direction, these are trajectories that have an angle that is close to pi. And so in that setting, or when theta is very close to pi, these are arcing towards the boundary when the boundary is arcing in the other direction. And so these trajectories are staying relatively close to the boundary, and so we get this caustic. It's obviously not a very rigorous way of talking about it, but that's sort of a geometric interpretation of it. And one interesting feature of magnetic billiards is that there can be caustics near the boundary, even if the boundary is allowed to be concave. So even if there's a point of negative curvature, then these caustics can still survive. And so there is an analogous magnetic Birkhoff conjecture that now says that circles are the only integral magnetic billiards. Okay. So next up, we have a big topic of my interest that I worked on for my dissertation. And this is what we call inverse magnetic billiards. And so what this is that this is a combination of both magnetic billiards and Birkhoff billiards, where now we consider the boundary of our table to be permeable. It's no longer a hard boundary with an angle of incidence, this angle of reflection. It's now seen as sort of a delineation between the interior of our table, which has zero magnetic field. And so our charged particle, our billiard ball, moves in straight lines. And as soon as it reaches the boundary, that magnetic field is instantly on, and this charged particle moves in a circular arc of the same magnetic, or the same Larmor radius mu. And so in this picture, this is sort of a typical orbit for an ellipse where we start with a point S and theta. Again, parameterize the boundary by arc length. We've got tangent vectors here. And L1 stands for the length of the billiard on the inside. Gamma here, this is the circular arc, or the length of the circular arc on the outside. And S corresponds to the area that is inside the circular arc, but outside the table. And so we sort of have a composition of standard billiards and magnetic billiards. And one thing that we can say is that because this circle, this Larmor circle, is tangent to this, if we were to take this ray from this billiard ray and extend it further, this circle is going to be tangent to this, to that line. And so what that means is that this billiard is always going to return to the interior of this billiard table. There isn't some possible way that that for some values of the magnetic field, this could move on a circle and somehow miss the table and encircle the table. The circle always has to be on one side of this line, and so it will always intersect the table again. There are applications of this inverse magnetic billiards idea in condensed matter physics and semiconductors. And the name inverse magnetic billiards first showed up in the literature of a system like this in 2003. So just like before, we can actually define, or from the previous picture, we can define this inverse magnetic billiard map, we'll call it T, as being the composition of the billiard map and the magnetic billiard map, but I'm putting a little star here on T2 to indicate that this is magnetic billiards on the outside of our set rather than on the inside. And in fact, there is a one-to-one correspondence with interior magnetic billiards and exterior magnetic billiards. And so a lot of the techniques for magnetic billiards will carry over to this, this inverse magnetic billiard setting. Just as before, this inverse magnetic billiard map T is also r-1 times differentiable if the boundary is r times differentiable. Just as before, we can extend this map to be the identity when theta is 0 and theta is pi, so motion stops. It's area preserving. And again, we have very different dynamics based on whether the Larmor radius is going to be in between or less than or greater than the minimum and maximum radii of curvature of the boundary. So just like in magnetic billiards, this map is sometimes a twist map. And we can specifically say that it's going to be when mu is smaller than the minimum radius of curvature. It was the opposite when it came to magnetic billiards. Just as before, this means we get infinitely many periodic orbits with rotation number p over q. And now we have a twist map that is Now, negative the Euclidean length of the billiards segment, minus L, the length of that circular arc on the outside, and then 1 over mu times S, that area on the outside. And that one over mu times S, this is really, this can be interpreted as a flux term. This is really just a strength of the magnetic field times an area term. And so we can really think of it as flux, the same way that we might teach our students in with surface integrals and multivariable calculus about flux integrals. So circular magnetic billiards, circular inverse magnetic billiards is just like the magnetic billiard setting, where we have a nice expression for this billiard map. Theta is going to be an integral of motion. And this map is going to be, this position coordinate is going to change to S plus 2r chi, where chi, from the previous slide, chi is the angle between the outgoing velocity vector here and the chord that connects the exit point and re-entry point. And so in this picture, we have 2 different period 9 orbits. And the big thing to notice about these 2 different orbits, aside from just how beautiful these pictures are, is that the picture on the left has an initial angle that is close to 0, and the picture on the right has an initial angle that's close to pi. And so what this means is in inverse magnetic billiards that we can think about these points as being ascending, or just being a small perturbation away from the billiard map when theta is very close to pi, because instead of reflecting at that point of reflection, there's just a small change in where it goes to next. And same thing over here, when theta is very close to pi, the billiard segment is the thing that does a lot of the action here. It still moves on a large circle on the outside, but it re-enters very close to where it exited. And so understanding this motion close to 0 and close to pi is useful when it comes to understanding caustics near the boundary, because we see that the billiard portion of this map is taking over rather than the magnetic portion. Oh yeah, and as I said before, this is an integrable map. So here's an example of a sample orbit inside an ellipse, where again it moves on a straight line and then moves on a circular arc on the outside. In orange, these are the centers of these Lamarr circles, and in red, we've got each focus of this ellipse. And so we can iterate this map several times and see what it looks like. This is now iterating that map 100 times and then 1,000. Again, these dark purple points are the points on the boundary. The exit and re-entry points on the boundary. Orange points are the centers of these Lamarr circles. So as we said before, we can now think about, usually we fix the strength of the magnetic field, but we can instead, if we were to say fix an orbit or fix sort of one iteration of this map and think about the magnetic field as changing, then as the strength of the magnetic field goes to infinity, then mu is going to go to 0, and this is going to limit to the standard billiard map. And at the same time, if the strength of the magnetic field goes to 0, then this Lamarr radius mu goes to infinity. And so this map really limits to the identity map in terms of changing this magnetic field, because it's now moving on a circle of a very large radius and coming back in very close to where it initially started on the opposite side from where it exited. Again, this is because it's now on a very large circle that has to be tangent to this billiard, this sort of interior straight line billiard at this exit point. So for inverse magnetic billiards inside an ellipse, here are 2 examples in the case when it's a twist map where we do have caustics. On the left, we can see it has a hyperbolic caustic. It's not confocal. We've got the foci of this ellipse here in red so that we can see where they are, but this picture on the right now gives us another convex caustic, but again, it's not confocal. Here's a slightly more detailed phase portrait for our inverse magnetic billiard. We have these period 2 orbits. There's a lot of invariant curves close to pi, and down here close to 0 as well. Here's a fun picture that is very Starry Night-esque of the phase portrait when mu is between the minimum and maximum radii of curvature. the orbits that correspond to some of these invariant curves are very interesting, and some of them have some almost polygonal caustics. I didn't include any of those pictures here, but they're very fun to explore. In the case when mu is larger than the maximum radius of curvature, we can see that these invariant curves are starting to fill up more of phase space, and the amount, sort of the measure that is chaotic is decreasing from where it was before. And when mu is much, much larger than the maximum radius of curvature, then again, the amount that is chaotic is significantly dampened down, and we have more and more invariant curves. So just like before, we can ask when caustics can exist in inverse magnetic billiards. So what changes now is that there can be interior and exterior caustics, because now the trajectory is no longer restricted to being inside of our billiard table. But what we're going to focus on is interior caustics. At the moment, I don't quite have a proof for an analog of the string construction. This is something that, if any of you have any great ideas for, I would be happy to listen. Similar to magnetic billiards, we can prove that in the cases when mu is smaller than the minimum radius of curvature and larger than the maximum radius of curvature and theta is near 0, then we're going to have caustics. And then also when mu is, or for all values of mu, when theta is very close to pi, like we saw earlier in the circular case, that when theta is close to pi, the billiard, the straight line part of the billiard is doing most of the action here. So we can also talk about, and one thing that's different here is that if the curvature vanishes of the boundary, then there are going to be no interior caustics. So this is something that's different from magnetic billiards, but the same as Birkhoff billiards. It is still possible for exterior caustics to exist, but those are a little bit harder to get a handle on. And just like before with magnetic billiards and Birkhoff billiards, there's a similar conjecture that says that circles are the only integrable inverse magnetic billiards. So with that, I'm about 3 minutes early, but I am going to end it there. Thank you.